Hello everyone, this is Team I'm Stuck, and we're gonna know after why we named it that way. Today we're gonna talk about local search and its applications. Before we proceed, let's imagine that we're building an AI system that chooses the best move out of all possible moves. Or we're building a scheduling system that ensures no student conflict while maximizing room utilization. And these problems are a type of optimization problems where our goal is to find the best option out of the vast set of options. However, as the number of states grows, the possible solutions can grow exponentially, and searching all possibilities will become impractical if not impossible. If we take the game of Go, for example, the number of possible states are 10 to the power 172, which is significantly larger than the number of atoms in the whole universe. So, one thing that could help us is local search. And these algorithms maintain a single node or state and searches by moving to the neighboring node. So at each state, we're trying to find if we can make the whole states better. Local search isn't useful in contexts like trying to find a path from our initial state to the goal state like A star or any of the pathfinding algorithms. But local search is very applicable when we only care about trying to find a solution rather than the path to it. And in these algorithms, we don't know what the goal looks like, and figuring it out is actually the heart of the problem. Let's consider an example where our goal is to find a way to place two scarecrows such that the distance from any plant to its nearest scarecrow is minimized. And there's multiple ways of calculating the distance, but let's try the Manhattan distance for example. And for this particular configuration of scarecrows, if we sum up all the distances, we get a cost of 17. But can we and how can we minimize this cost? If we take the scarecrow example or any similar examples, we can actually formulate it with the state space landscape, where each point on the x-axis represents a particular state that our world could be in. And in the previous example, it's the configuration of the two scarecrows. And each point on the y-axis represents a particular cost or objective function that we're trying to accomplish. And generally, we want to find either the global maximum, which is a single state whose value is higher than all other states that we can possibly choose from, or in the reverse problem, where we want to find the global minimum, which is a state that has a value that is lower than the other possible states. And in our previous example, we want to find the global minimum, which minimizes our cost function. We'll start by hill climbing, which is the one of the simplest algorithms that we can use to implement the idea of local search. And we will start at the state that we choose, and then we consider the neighbors of those states. And if we're trying to maximize our function, we will pick the highest neighbor and so on until there's no better option. And if we're trying to find the global minimum, we will keep picking the lowest neighbor until we can't find any better. And in this image, we consider both neighbors, and we pick the neighbor that maximizes or minimizes our cost. It depends on our objective function. And in the case of the scarecrow, we want to minimize it and try to find a neighbor that makes our total cost lower. And the pseudocode for hill climbing algorithm looks like this. We have a function hill climb that takes the problem that we're trying to solve, and generally we start with an initial state called current, which is keeping track of the initial configuration of the two scarecrows. And now we loop until the algorithm terminates. We check all the neighbors of my current state, and we will pick the neighbor with the highest value or lowest, depends on our objective function. If this max or min neighbor is not better than our current, we will return the current since we can't find any better options. But if my neighbor is better, we will move to that neighbor and keep going until we can't anymore. In our scarecrow example, at every state we check if we can do better by just making small incremental changes and by moving to a neighbor that will increase our objective function. or decrease it in case of minimization. If you keep going, at this point, our algorithm will terminate as there is no neighbor that we can move to that is going to improve our cost. However, is this the best that we can do? And the short answer is no. One of the way that we can do better if we move the left scarecrow diagonally by 1 square, which we can see the total cost is 9 instead of 11. However, this neighbor wasn't part of our neighbor options since we can't choose diagonal neighbors. And this is a limitation to the hill climbing algorithm as it won't always give you the best optimal solution. If we're trying to find a global maximum, a concern will be that we could get stuck at one of the local maxima. A local maxima is any state whose value is higher than any of its neighbors. And we can see from the graph that there are multiple local maxima that we can get stuck into. And likewise, in the case of the scarecrows, we're trying to find the global minimum, and we can get stuck at any of the local minima. It all depends on where we start. As we saw earlier, because of our limitation, multiple hill climbing variants have been taken into consideration, and we saw the steepest ascent or steepest descent, which chooses the best or the highest value or lowest value neighbor. And there are stochastic variant, which chooses randomly from the higher valued neighbors. So if you have 5 neighbors that they are all the same value, we randomly chooses one of these neighbors. Another one would be first choice, which chooses the first highest value neighbor, and random restart, which is very useful, where we conduct hill climbing multiple times, each starting at a different state, which might lead us to a better or maybe the global maxima or global minima. And local beam search, which chooses the case highest value neighbor. And we're going to talk about local beam search later on. Another algorithm for local search is simulated annealing, which the name comes from the physical process of annealing, where we have a system of particles, and when we heat up that system, the particles will move more randomly, and when we cool down, the system will eventually settle into some final position. And that's the general idea. We're going to simulate that process where we first move more randomly and then settle at our ultimate solution, and this is very helpful. Since hill climbing will always pick the state that will increase our objective function, but we can't always make good moves to find the global maximum or minimum. We sometimes need to make a move that might make our situation worse, such that later on we can find our way up to the global maximum. And as we can see in the picture, we don't want to always go right. Sometimes we can make a bad move, which is going left, and which later on will take us into the global maximum. So in summary, early on we are more likely to accept neighbors that are worse than our current state, and later on we are less likely to accept neighbors that are worse than our current state. And the pseudocode looks like this. First, we have a function simulated annealing, which takes a problem and some maximum number of times that we might want to run the simulated annealing process. We'll again start with some current state, and now we need to repeat the process over and over for a max number of times, where we first are going to calculate the temperature, where the temperature function takes the current time t, and starting at time 1 to max, and gives us the temperature which will be higher early on and lower later on. And then we pick a random neighbor from our current state, and we no longer pick the best neighbor as in hill climbing. We're going to calculate delta E, and E is for energy, for how much better our neighbor is than our current state. If delta E is positive, the neighbor is better than our current state. If it's negative, it's worse. If delta E is better, we will update current to be the neighbor. But now the difference is that we sometimes want to make a move that might makes our situation worse in order to dislodge ourselves from our local minima and local maxima to find the global maximum and the global minimum. We then calculate e to the power delta e over t, which is one of the most promising ways to calculate the probability. And at the very end, we just return the current state. These algorithms are actually good in finding a good solution for the traveling salesman problem. It might not find the optimal solution, but it approximate a good answer for it.
I will explain the other variants of local search algorithms, taboo search, and local bin search. Let's start with the taboo search. Imagine a problem where we aim to minimize a function, such as finding the shortest path or minimum cost. What is the challenge? Our solution space is filled with traps known as local minima. In this graph, the dips represent these local minima suboptimal points where many traditional algorithms might get stuck. But the ultimate goal is the global minimum, the lowest point on the curve. Here's where Tabusa shines. It uses a memory-based mechanism called the tabu list to track recently visited solutions and avoid revisiting them. So this allows the algorithm to escape local minima by sometimes accepting worse solutions temporarily, as indicated by the blue arrows, leading to broader exploration. Eventually, it uncovers the global minimum as shown by the red arrow. Fred Glover deployed this approach in the 1980s for combinatorial optimization, and its key idea is overcoming traditional search limitations by enhancing exploration and exploitation within the solution space. Let's break down these key components. For the neighborhood search, this generates potential solutions near the current one, helping explore nearby possibilities. For the taboo list, this memory structure ensures recently visited solutions are off limits, which prevents cycles. For the aspiration criteria, if a taboo solution significantly improves the result, the taboo state is overridden. For the stopping conditions, iteration stop when a predefined stopping condition is met, such as a maximum number of iterations or no improvement after a set number of iterations. Now let's walk through the process how taboo search works. We start with an initial solution, our starting point in the search space. Next, we explore the neighborhood, generating potential solutions through modifications like swapping variables, and each solution is evaluated using an objective function such as cost or distance, and then the best admissible solution is selected, considering the taboo list and aspiration criteria. After that, we check stopping conditions. If they are met, we end the process. Otherwise, we continue and update the taboo list, making the current solution as taboo to avoid revisiting it. Here is a visual summary of the taboo search workflow. For the initial solution, this process begins with an initial solution. For example, in the traveling salesman problem, this could be a random sequence of cities to visit. This initial solution serves as the starting point for the search. From the current solution, we explore the neighborhood by generating candidate solutions. For instance, we might swap two cities in the traveling salesman problem to create a new path. And the candidate list includes all possible moves or transitions from the current solutions. Next, we evaluate each candidate solution based on an objective function, like the total distance traveled in TSP. This step helps identify which candidates are most promising. Among the evaluated solutions, we select the best admissible solution. Admissibility means the solution is not on the taboo list unless it meets the aspiration criterion. For example, if a taboo move results in a significant improvement, we can override its taboo status. At this stage, we check if the stopping criteria are met. These criteria could include a maximum number of iterations, a time limit, or no significant improvement over several iterations. So if the stopping condition is met, the algorithm terminates, and the current solution is returned as the final solution. If the stopping condition is not satisfied, we update the taboo list to include the current solution or move. This prevents the algorithm from revisiting recently explored solutions. And the aspiration conditions are also updated, allowing those taboo moves to be considered if they lead to better results. The process then looks back to generate a new candidate list based on the updated solution and taboo list, iterating until the stopping condition is met. This is how taboo search works in minimum spanning tree. So the algorithm starts by generating an initial spanning tree that connects all nodes with the maximum cost. After that, in iteration 1, the cost is calculated as 75, and it represents a low-gate optimum because constraint may not yet be satisfied or explored. The taboo search algorithms modify the solution by deleting one edge and adding another edge. For deleting one edge AB with a cost of 10D and adding another edge CE with a cost of 30D in iteration 2. And this step introduces a new solution with a higher cost, which is 85, allowing the algorithm to explore outside the low-gate optimum. And the modified edge CE is marked as taboo, forbidden temporarily to prevent the algorithm from cycling back to this solution immediately. And in iteration 3, we found better solution. The algorithm evaluates another set of neighbors while respecting the taboo list. It overrides the taboo state if the new solution significantly improves the objective. For example, deleting edge CE and adding edge CD, which is cost 15 now. So the new score is reduced to 70, which becomes the global optimum for this problem. And for the final iteration, aka final solution, after separate iterations, the algorithm concludes that no better solution exists, which is cost equal to 70. The optimal spanning tree is now determined. So what does taboo search mean here is that it avoids revisiting the same configurations by using a taboo list, and it allows non-improving moves to escape low-gate optima, ensuring exploration of the solution space. In this example, the algorithm modifies the graph iteratively to balance reducing costs and satisfying constraints. And each modification is guided by the taboo list and aspiration criteria to allow better solution despite being taboo. And for the key strategies in taboo search, forbidden strategy, which controls what enters the taboo list, and freeing strategy means it manages when items leave the taboo list. And for intensification and diversification, taboo search balance those two strategies. For intensification, it refines the search around the best solutions found using mechanisms like aspiration criteria to allow revisiting taboo moves if they lead to better solutions. Here, intensification means the right side, the red bars, solutions. Those red bars represent solutions that are neighbors of the best solutions found so far. And for the diversification, it avoids revisiting recently explored solution or region thanks to the taboo list and diversification strategies. And the blue bars represent diversification in explored or unvisited areas of the solution space. And it encourages the algorithm to move to new region of the search space to avoid getting stuck in low-gate optima. And the person is with magnifying glass represents the algorithm heuristic, which decides where to focus attention, either intensifying the search around elite solutions or diversifying to explore new areas. Now let's move to the low-gate bin search. Let's start by understanding what low-gate bin search is. Low-gate bin search is a heuristic search algorithm that maintains a fixed number of candidate solutions, what we call bins, at each iteration. Unlike greedy search, which focuses on one path at a time, low-gate bin search simultaneously explores multiple paths in parallel. If you look at the diagram here, you will see the comparison between greedy search and bin search. So in greedy search, the focus is on a single path, which might lead us to a suboptimal solution if that path reaches a dead end. On the other hand, bin search evaluates multiple paths, ensuring that we keep exploring promising areas of the solution space. The key here is the concept of K candidates or bin weights. At each step, we only retain the top K solutions based on heuristic evaluation, and this strategy reduces the risk of getting stuck in locate optima by diversifying the search space. For the key features of locate bin search, it focuses on multiple promising paths instead of one for their search strategy. And exploration, it broadens the search by discovering new and visited areas and avoids locate optima by introducing diversity. For the exploitation, it refines existing solution by focusing on immediate neighborhoods, and it converges to the best local solution. And local bin search combines exploration and exploitation effectively for better outcomes. Let's break this process step by step. In the top row, we have K initial solutions labeled as A1, B1 to K1. These represent the starting points of our search process. These initial solutions can be generated either randomly or heuristically depending on the problem we are trying to solve. For example, in the traveling salesman problem, these could be random routes connecting all the cities. From each initial solution, the algorithm generates a set of neighbors. The arrows in the diagram show how each solution expands into a series of possible candidates in the second layer. For example, if we are solving a traveling salesman problem, these neighbors could be new routes found by swapping two cities in the current route or changing the order of visits. This step ensures we explore possible improvements or variation for every initial solution. Now, out of all the neighbors generated in step 2, the algorithm evaluates each one using a heuristic function. From the expanded pool, we retain the top K solution with the best scores. These are shown in the second row, A2, B2, and K2. This is a critical step when we prompt weaker candidates and focus our computational efforts on the most promising options. By maintaining diversity among these K solutions, we reduce the risk of converging prematurely to a suboptimal solution. And the final step 4, repeat until a stopping criteria is met. The process continues iteratively. Each set of K solution generates their neighbors, which are again evaluated, and the best K are retained. We repeat this loop until a stopping condition is met. For the common stopping conditions, they include finding an optimal or satisfactory solution, or reaching the maximum number of iterations, or exhausting computational resources. The arrows in the diagram demonstrate how the process repeats, moving layer by layer, refining the solution space at each step. So this locate bin search process ensures a balance between exploration by generating diverse neighbors and exploitation by focusing only on the most promising solutions. Now let's connect this concept to the traveling salesman problem. Imagine a salesman who has to visit several cities and return to the starting point, minimizing the total distance traveled. This is a classic optimization problem. Locate bin search can be applied effectively to these problems. Here how it works. Let me see. In this step, we initialize two random routes, A, B, and then C, D. Let assume K equal to 2 and start with randomly K generated states. Here, generating neighbor step, right? Each route generates multiple neighbors, for example, swapping city or reversing sections of a route. In this case, the new neighbors are shown branching out from each initial route. After that, we select the best neighbors. From all generated routes, we select the best K routes, those with the shortest distance. These selected routes are highlighted and retained for the next iteration. And the process continues until we converge on the optimal solution. In this case, the best route covering all cities is A, B, C, D, and then A, B, C, D, A. By keeping multiple bins active throughout the process, local bin search ensures that we don't get stuck in a poor solution. Now let's take a closer look at the strengths and weaknesses of both tabu search and local bin search. Each of these algorithms has unique characteristics that make them suitable for different types of optimization problems. This table clearly lays out their respective advantages and limitations. Starting with the tabu search, one of its key strengths is its ability to avoid cycling and revisiting previously explored solutions using the tabu list. This feature ensures that the algorithm doesn't get stuck in a loop, which is particularly useful for problems with complex solution spaces. Tabu search is also highly customizable, and its parameters can be adjusted to fit a wide range of problems. For instance, if you are solving a job scheduling problem, you can fine-tune the tabu list size or tenure to suit your requirements. On the other side, tabu search can become computationally expensive, especially for large problems. Why? Because it evaluates all neighbors in each iteration. This means as the size of the problem grows, the computational resource required also an increase. Another challenge is that careful tuning of parameters like the tabu list size. Without proper calibration, the algorithm performance can be suboptimal. For the local bin search, so for their strengths, switching its ability to explore multiple areas of the solution space simultaneously is a standout feature. This diversity allows it to converge faster for specific problems by dynamically exploring multiple paths. For example, in the traveling salesman problem, local bin search can examine several routes at once, making it less likely to get trapped in a local optimum. However, local bin search isn't without its challenges. The computational costs increase as the bin size grows. Imagine managing a large team of problem solvers. Coordination and evaluation becomes resource intensive, and additionally, focusing too much on the most promising bins might lead to premature convergence where the algorithm makes better solution by narrowing its scopes too quickly. These strengths and weaknesses give us a good idea of the scenarios where these algorithms can excel. And now let's analyze their computational complexity and trade-off in these slides. So for tabu search, the computational complexity depends on two key factors: the size of the neighborhood, which is the number of neighbors evaluated by iteration, and the length of the tabu list. If we denote the neighborhood size as n and tabu list length as t, the complexity by iteration is approximately bit over n dot t. This means that computational costs increase linearly with the number of neighbors and the size of the tabu list. Why tabu search excels in escaping local optima by exploring a broader solution space? This came at a high computational cost. However, this trade-off is often justified for problems where finding a globally optimal solution is critical. So the key takeaway here is that while tabu search may be computationally expensive, its ability to escape local optima makes it highly effective for combinatorial optimization problems. Now move on to the local bin search. In this case, the complexity depends on the bin width, denoted as K, the size of the neighborhood explored for each bin, represented as N. The overall complexity by iteration is approximately bit over K into N. This means the increase in the bin width results in a linear increase in computational cost. For the trade-off, it offers a different compared to tabu search. A higher bin width enhances the algorithm ability to explore diverse solution spaces, increasing the likelihood of finding an optimal solution. However, this comes at the cost of greater computational requirements. On the other hand, a lower beam width reduces computational costs but increases the risk of premature convergence, while the algorithm settles on suboptimal solutions too early. So the key takeaway here is that local beam search is less computationally intensive compared to tabu search. However, it requires careful selection of the beam width to balance exploration and exploitation effectively. By fine-tuning this parameter, you can adapt the algorithm to the specific needs of your problem. So the key takeaways for both such algorithms, tabu search is particularly effective for the structural problem like job scheduling or vehicle routing, and its memory-based exploration allows it to escape local optima. For the local beam search, it shines in scenarios where exploring diverse paths is critical. By managing multiple beams, it can efficiently handle problems like path finding or optimization. But again, the computational costs associated with higher beam widths and the risk of premature convergence are trade-offs to consider.
Evolutionary algorithms. What exactly are evolutionary algorithms? Well, they are essentially seen as variants of stochastic beam search motivated by the metaphor of natural selection in biology. Now, the term stochastic means randomly determined or having some random probability distribution. This means that there is an element of randomness to the search. The metaphor we're discussing here, the metaphor of natural selection, is that there is a population of individuals or states in which the fittest or highest value individuals produce offspring. These offspring, or successor states, populate the next generation in a process known as recombination. In essence, evolutionary algorithms mimic or imitate the process of evolution and how organisms evolve over generations in nature. Now, there are several forms of evolutionary algorithms: the size of the population and the representation of each individual. Individuals are represented as a string or a finite alphabet, which is typically a Boolean string in genetic algorithms. For example, DNA is a string of a finite alphabet. It iterates only over the given letters A, C, G, T. In evolution strategies, the individual is represented as a sequence of real numbers. However, in genetic programming, the individual is instead represented as a computer program. Both are different types of evolutionary algorithms suited to different purposes and problems. Genetic programming evolves computer models or programs to solve problems. Evolution strategies focus instead on optimizing real valued parameter vectors in order to solve continuous optimization problems. Now, here we have an example of a genetic algorithm. We first start with our initial population of solutions, represented as a sequence or chromosomes. They are ranked by a fitness function, which evaluates how well each solution solves the problem. This results in pairs for mating in the selection process. For example, 23 and 24, in this case, represents high fitness scores. Now the mixing number, P, in this example, is a representation of how many parents combine to produce offspring. The standard and typical value for this is 2, meaning 2 parents contribute to the next generation. Now there are a few special cases where this doesn't occur. When P equals 1, we have asexual reproduction, which is similar to a stochastic search. In the case of P greater than 2, it is a rare case in nature, but considered easy to simulate computationally for unique applications. The reason behind P equals 1 being a stochastic beam search is because there is no usage of crossover, meaning mutation or randomness is applied to avoid getting stuck in the local optima. Now, moving forward, the selection process involves choosing parents for the next generation based on their fitness scores. Here, Fitter individuals are favored, but some diversification is allowed, mimicking the survival of the fittest effect we see in evolution. How we do this is by selecting individuals with their probability directly proportional to their fitness score. We then randomly select individuals and select P most fit ones as parents with the assumption that N is greater than P. Now, the recombination procedure typically involves the selection of a random crossover point on each of the parent strings. Two offspring are created, one with the first part of parent 1 and the second part of parent 2, and the other vice versa, so the second part of parent 1 and the first part of parent 2. Now, the mutation rate determines how frequently offspring experience random changes in their genetic composition. How this is done is that each bit or gene in the offspring's representation has a small chance of being flipped or altered based on the mutation rate. Essentially, selection ensures fitter individuals are more likely to contribute to the next generation, while randomness allows diversity. Crossover recombines traits from parents for new solutions, and mutation adds that element of randomness to help explore unexplored regions of our solution space. Now, here's an example of the algorithm I just gave you an example of in pseudocode. The population is an ordered list of individuals. The weights is a list of corresponding fitness values for every individual, and the fitness is a function to compute how good these values are. To briefly summarize, our algorithm repeats until one or two conditions are met. A solution is fit enough based on the fitness function or maximum time or iteration time is reached. Now, our weights are calculated by assigning probabilities to individuals in our population based on their fitness. Our weighted random choices function randomly selects two parents, with the more fitter individuals being more likely to get chosen. The reproduction function combines genetic material from two parents to create a child solution. The length of parent strings gets determined by the line set by n to be the length of parent 1. A random crossover point is made called C, choosing between 1 and n, and then a child is made by appending the first part of parent 1 to the second part of parent 2. Occasionally, a child may undergo a mutation due to some small random probability, which alters its genetic material and allows diversity, like we mentioned. A new population is now created in each generation by iterating over the current population. Here, children are added until the new population is the same size as the old one. Until some individual is fit enough, or enough time passes, we then return the best individual in the population based on fitness. Now, let's go over and discuss elitism and culling. Elitism is the practice of only including a few top-scoring parents from prior generations into the next one. What this does is ensure that the overall fitness will never decrease over time, allowing only the best from each generation to be carried over and potentially allow better characteristics. Now, culling is a bit more drastic. This practice involves discarding individuals below a certain threshold. This can lead to a sped-up convergence towards an optimal solution by preventing a loss of important genetic information. Now, this all ties back to the theory of evolution and the concept of it. Developed by a man known as Charles Darwin On the Origin of Species by Means of Natural Selection in 1859, and independently by a man named Alfred Russel Wallace, the central idea is that variations will occur in reproduction and are preserved in successive generations based on how crucial their impact is on reproductive fitness. In short, variations that have greater benefits are more likely to pass down to future generations. His theory was developed with no prior understanding of how the traits were inherited, Darwin's that is, and it was only later through Watson and Clark in 1953 that we identified the components in the DNA molecule to help us understand it more and learn more about concepts like mutations and crossover. Now, something to note is that the principal difference between stochastic beam search and evolution is the use of sexual reproduction. Successors aren't generated from one individual, but multiple. Furthermore, the mechanisms of evolution are very large and rich, more so than allowed by the genetic algorithms. Mutations can involve duplications, reversals, and large movements of DNA chunks. Genes themselves also encode the mechanisms, as opposed to genetic algorithms, where they're considered a separate program. In conclusion, evolution itself is a complex process. It is one with many different factors to consider. And now we will discuss the applications of local search. Now, firstly, how does taboo search help in job scheduling? We first start with an initial schedule and explore different ways to rearrange the jobs. Taboo search avoids revisiting poor schedules using the taboo list and overrides it only when a better schedule emerges. Over time, it allows us to find an optimal or near optimal schedule which balances deadlines, resource allocation, and machine usage. This aims to help us address the issue of job search scheduling and its challenges and constraints. Specifically, it escapes local optima and handles dynamic constraints. Here is an example of a schedule, as you can see right here below, after applying taboo search. And its real-world applications are in automotive production lines, where parts have to be processed in multiple machines in a very specific order. Now, real-world applications of local search. There is a variety of fields where it has real-world usage. In robotics, it helps autonomous robots navigate obstacles while finding the shortest path to the goal. In a variety of games, such as strategy games like chess, it helps find optimal moves against opponents. It also helps improve delivery routing in logistics and supply chain industries to help minimize travel time. Lastly, kind of going back to the topics we discussed earlier, in DNA sequencing, it helps assist in aligning DNA sequences by finding ideal and optimal matches between large data sets. There is a plethora of different ways local search has helped us, and it's played a crucial role in our lives. So with that said, thank you for watching our presentation. Thank you for listening. We very much appreciate it. And here is our resources.